Hello dear students. Today we will be starting with the first lecture for EE 203 measurements and instrumentation. So measurement is the act or the result of a quantitative comparison between a given quantity and the quantity of the same kind chosen as a unit. So you have a quantity that is being measured, so you are comparing that quantity with something that is already there of same quantity, say current. So you are measuring a current through a circuit. So you need to measure this using some instrument which is already showing that particular quantity. So it's basically comparison between two quantities. So you're comparing the given quantity with some other value. So the result of the measurement can be in the form of a deflection in case of analog instruments. So it can be in the form of values as digital instruments show as digits, or kind of ratio between unknown quantity and the standard. Now the instrument that we use is used for comparing the unknown quantity with the unit of measurement or the standard quantity. So you have a standard quantity or a general unit, and you are comparing the unknown quantity with that, and you are finding or arriving at the result. Now what is a standard? A standard is a physical representation of the unit of measurement, or it can be its submultiples or multiple values. So we'll see in detail different types of standards. So the standards are generally classified into four. Those are international standards, and you have something known as primary standards, secondary standards, and finally you have working standards. So the international standards are defined by international agreement. So these are internationally accepted, and these indicate the maximum possible accurate value of a particular measurement with the technology that is available. So it is the best standard that is available in the world. These are periodically checked and evaluated with reference to the absolute units or SI units or fundamental units. So you have some fundamental units, or based on those fundamental units, these international standards are periodically verified and evaluated, and they are kept intact. Now these are available and maintained at the International Bureau of Weights and Measures, and these are not available to ordinary user. Okay, so these are basically standards which are kept at that particular bureau, and these are not available for calibration purposes. Then you have primary standards. These primary standards are maintained by different national standard laboratories across the world. Again, these primary standards are independently calibrated by absolute measurements at these different national laboratories. So suppose India is having Bureau of Indian Standards, which is the national standard for measurements in India. So they'll be having a measurement standard, and they'll be having primary standards, and these primary standards will be calibrated at this BIS, which is a national laboratory. And you have such national laboratories across the world, and average of such values or measurements are compared, and you arrive at a primary standard. Again, these are not available outside the national laboratories. The main purpose of this primary standard is to verify and calibrate secondary standards, which are the basic reference standards used in industrial measurement laboratories. So you have an industrial measurement laboratory, so they'll be using some standard to calibrate their measurements or readings. And this particular industry will be responsible for the accuracy of the standard, the calibration of the standard, as well as maintenance of this particular standard. So this primary, secondary standards will be calibrated against the primary standards for accuracy. Now the secondary standards are sent to national standard laboratories on a periodic basis for calibration and comparison. So suppose in India you have some national standard, and the secondary standards across different industrial laboratories are compared with the primary standard at the national laboratory. Then ultimately you have the working standard, which are the principal tools which are used in a general laboratory. So these are used to check and calibrate the general instruments that are used in different laboratories and also in industries. Suppose you are trying to manufacture a resistor. In an industry you are trying to manufacture a resistor. So you are specified that you are going to measure or you are going to manufacture 100 plus or minus 5% ohm. This is a value of resistor that you need. Now how will you say that the particular resistor that is being manufactured is having this value, say 100 ohms plus or minus 5%? So you will be having a standard resistor which is kept at this particular laboratory or particular industry, and this particular standard is known as the working standard, the standard resistor. So this the resistor that is being manufactured will be compared against this particular standard that is available at that industry. Okay, and if the value is falling within this particular range, you can say that this particular resistor that is being manufactured has crossed the quality check and it is ready to be supplied out. Okay, so that's how this particular process works. So these are all different standards that are available, and these standards are generally used to calibrate different instruments that we use. Okay, we'll see what the process of calibration is, which we'll see in detail. Okay, this is basically trying to check the accuracy of a particular instrument. Periodically we will be doing the calibration, and you must have done this calibration in your +2 classes. Now while moving into measurements or electrical measurements, we have two terms which are known as the true value and the measured value. Now the true value is the real value that is expected, the actual current that is, suppose you are measuring the current, so it will be the actual current that is flowing in that particular circuit. It is the true value. Now what will be the measured value? It is a value that is being indicated by this particular meter, by the particular instrument that is being used. So this true value may be equal to measured value. It may be different when compared to the measured value, or the measured value will be different from the true value if you have some errors in the measurement. Now we have few characteristics that we need to establish before we move on to the details of different instruments, and these characteristics form the basic for selection of different instruments for different purposes. So these include accuracy, precision, linearity, sensitivity, resolution, dead time, and dead zone. We have few others also, but major ones are these. Now accuracy indicates the degree of closeness of a quantity to the true value. Here capital A T represents the true value and capital A M represents the measured value. Now the true value is 1.6 volt and the measured value is 1.7 volt, suppose. So this is the value that you actually need to get, but your instrument is indicating 1.7. Okay, so your true value, measured value can be different from true value. It happens if your instrument is not accurate. So if you are saying that your instrument is accurate, you should be getting your measured value equal to the true value. In such a case, you can say that your instrument is highly accurate. Now we will look at a case. You have a pressure gauge with a range of 0 to 10 bar, and it has an inaccuracy of 1% of full scale reading. That is, it has an error of 1% of full scale reading. What is the maximum measurement error that is expected for this instrument, and what is the likely error as a percentage of the reading if it is measuring 1 bar? Okay, so you have 0 to 10 bar measured, and you have 1% error with respect to full scale reading. So what is full scale reading? It is a maximum reading. So you have 10 bar is a full scale reading. So what will be the error? Error will be 1% of 10 bar. So that will be 0.1 bar. 1% of 10 bar is 0.1 bar. So that is the error that you can expect once you are measuring or once you are using this particular pressure gauge. Now, what is the error that is expected when you are measuring 1 bar? What is the maximum error? Suppose you are measuring 1 bar. You are trying to measure 1 bar and the error is already we are saying that your maximum error is 0.1 bar. So once you measure 1 bar, if you are having 0.1 bar as the error, what will be the percentage of error? So once you are measuring 10 bar, you are getting 0.1 as the value, absolute value, which is 1%. So when you are measuring 1 bar, the maximum error that will be 10%. How will you get 10%? Because 0.1 bar is a 10% of 1 bar. Okay, so that's how you get 10%. Okay, so once you are measuring 1 bar, if you are having a maximum error of 0.1 bar, it will be 10% error. Okay. Now, precision. What is precision? It is the most repeatable or reproducible value out of a set of records. Okay, so you have precision and accuracy being compared here. So here you can see that this particular, in this example, this white dot shows the different readings that you are obtaining or the different set of experiments that is being conducted. So here you can see that you are expected to hit the center. So out of 4, in this case it is hitting the center all the 4 times, so it is accurate. It is reading the exact value, the required value, and it is precise also because it is reproducing the same value again and again. So it is precise. Here you can say that in the second case it is precise. You are getting some value continuously, you are getting a value repeatedly, but it is not accurate because accuracy is defined at the center, or you need to get the value at the center, but it is precise but not accurate. The third case, it is not accurate, it is not precise. You are getting somewhere here. It is not accurate, it is not precise. Here also, this is accurate because you are getting some value close to the center. You are getting some value close to center. You have some error, but still it is accurate when compared to the other case. You are getting value close to center, but it is not precise because you are not getting the value repeatedly, or you are not able to reproduce the value again. And in the last case, it is not accurate or not precise. Even you are getting one value outside the entire range. So this is not accurate and it is not precise. So precision simply means that are you able to get the values repeatedly, or are you able to reproduce the values again and again. So the accurate instruments may be precise. So here your accurate instrument is precise also, but precise instruments may not be accurate. Here you can see that this particular instrument is precise, but it is not accurate. It is showing wrong reading again and again, so it may not be accurate. Now the repeatability is when can you say that a particular instrument is showing repeatable readings? So the same input is being applied for a short period of time, and under same measurement conditions, you are getting the same result. Input is same and the measurement conditions, instrument, observer, location, and all the conditions are same, and if you are able to get the same result again and again, you can say that your property of repeatability is valid. Now can you say that it is reproducible? The result is reproducible for a particular instrument. Say input is same, but there are changes in the method of measurement. Say observer might change in your measurement instrument. The particular instrument might be replaced with another of the same kind. Say location, then temperature, time of measurement. Such different conditions might change, and even if you do the measurement morning, evening, or night, if you are able to reproduce the same result, such a condition is known as reproducibility. Now we'll have a quick comparison. You have two instruments A and B. So this is a true value, or the expected value is 2 ampere, and instrument A is having 6 readings, and out of the 6 readings, the 4 readings are showing 1.9, which is close to the true value. So you can say that your instrument is somewhat accurate and precise because it is indicating 1.9 4 times. So it is precise also as well as accurate. But if you have an instrument B which is used to measure 6 readings, the same under the same setup. So here you can say that the instrument is showing 1.54 times. It is precise, but it is not accurate because accuracy is defined at close to 2 amperes. So it is having accurate value only twice. Majority of the values are not accurate. So it is precise only, it is not accurate. This particular instrument B is not accurate. Now you have another property known as linearity. That is, your output should be following the input. You should have a linear relationship between input and the output, or the input and the measured shown quantity. So output here indicates that the one that is being shown or indicated by the instrument. Here you can see that two types of ammeters are here. This is a DC ammeter, first one, and this is an AC ammeter. Here you can see a sine wave is being shown, so this indicates that this is an AC instrument. Here you have a plain line is shown, so that indicates it's a DC instrument. Here you can see that your scale is uniform throughout. All the divisions are uniform. So if you are going to measure any reading, you can get it accurately. Suppose you take the second case. You are going to measure 5 ampere here. Where is 5 ampere? Here you have 0, this is 20, and here you will have 10, and 5 will be between 0 and 10. So here you don't have any indications also here. So you are not able to read 5 ampere AC using this instrument. So if you are going to read, or if you are going to use a particular instrument for reading 5 ampere, it has to be from 0 to 10 ampere range. So if you are using an instrument from 0 to 10 ampere, 5 ampere will be somewhere in the middle of this region. So you are able to measure it clearly. Again, you can see that you have a non-linear distribution of these indications. So from 0 to 40, you are taking this much space, and from 80 to 100 you have this much space only, but from 40 to 80 you are having a larger area, larger distance being covered by the pointer. So you can say that this region is linear, and the end region here and the starting region here is non-linear. Okay, and from the graph you can say that you should have once you are providing an input, you should get correspondingly proportional output. Once the input is increased, proportionally the output also has to change. Here output indicates that the pointer that is being deflected, that deflection has to be linearly related to the input being measured in case of analog instruments. So you have to choose instruments in such a way that the pointer will be in the linear region. So if you are going to measure 5 ampere, choose an instrument for 10 ampere range so that you can easily measure 5 ampere in the linear range. If you are having DC, you have no such issues generally because already your scale is linear. And why do you have a linear scale in DC and a non-linear scale in AC? We will see that in the coming lectures when you deal with these instruments in detail. Then sensitivity is the measure of change in instrument output to the unit change in input. That is, when the input is changed by 1 unit, how much the output is being changed, or can be rather called as the slope of the line. If you have a linear scale, your sensitivity is 1, and if you have a non-linear scale, your sensitivity varies throughout the scale. How the output is, or the responding with respect to input, that is being given by the sensitivity. Then you have resolution, which is the smallest output that can be detected, certainty or clarity, that is, or the smallest change in input that can be detected. So that is given by full scale value divided by total number of divisions. In this example, your full scale value is 3, and what will be the total number of divisions? You have 1, 2, 3, 4, 5, here 5. So total divisions is 20. And you can say that your resolution is 0.15, suppose this is volt, so 0.15 volt. So the smallest output that can be shown by this particular scale is 0.15. Suppose instead of 20 you had say 30 divisions, so the resolution will be 3 divided by 30. So in such a case your resolution will be 0.1. So you are able to show 0.1 in this particular reading. Or you can otherwise say that it is the smallest what is this particular division, smallest division that is there in this particular scale, 1 division. That is given by the resolution. As the number of divisions increases, the resolution improves. Though the magnitude of resolution has decreased from 0.15 to 0.1, the resolution has improved. That is, you are able to measure smaller inputs or able to show smaller values. So you have more resolution for that particular meter. Now, the next one is a dead time. Dead time is the time required by the meter to respond to a change in the input or the measured quantity. Okay. In certain instruments, even if you increase the input, the meter may not be reading at that time. Only after some lag, your instrument starts to read, and such a scenario is called as the dead time. And dead zone is the largest change in input quantity for which there is no output of the instrument. So here you can see that from 0 you have increased your input. Even if you are increasing your input, your output is not changing. So at this value, when you are reaching this value only, you are getting an output. So this particular zone is known as dead zone or dead band. So it can be in both directions. If you are increasing in the other direction also, so this particular region is known as dead band or dead space or neutral zone, or it is also known as dead zone. So in this example you can say that for instrument A there is no dead zone, for instrument C there is no dead zone, for instrument B there is some dead zone available. Your instrument A is linear, B is linear, but B is having dead zone. Though C is having no dead zone, it is not linear. It is not linear. The relationship between input and output is not linear. Okay, so in such cases you have different meters available. So this dead zone has to be minimum for effective response of the meter. So once your meter is showing some response, the dead zone has to be minimum. That is, whenever your input is increasing, at that time itself your output also should respond. Whenever your current is being flowing in the circuit or current is flowing in the circuit, the meter has to indicate that particular current. So with this, the different chiara are explained. So we'll see the continuation in the next lecture. Thank you.